Greetings to you, ladies and gentlemen. Before you is Mujela Manu, and thank you for being here with us today. We are here to share with you a presentation based on the removal of chromium and bacteria from wastewater using diethylamine functionalized Moringa oleifera.
Hello guys, my name is Kumbuzo Kanyeli.
Hello guys, my name is Beyonce Maili.
Hi guys, I'm Gwanele Ting.
Hey guys, my name is Sandy Swamsho.
Population has increased rapidly for the past years. The expeditious increase in population has led to a huge demand of fresh water. In today's generation, fresh water is now considered a scarce resource. Economical development such as industrialization and urbanization has surfaced with the disposal of different water pollutants. The different types of water pollutants that are being disposed to our environments are voltaic organic compounds, toxic chemicals, and also heavy metals. Now, in this case, we are going to dwell much on the heavy metals that are being disposed to our environment. For example, we have our chromium 6, our zinc, and also our copper. Now, in this case, chromium 6 is the most toxic pollutant to the environment. It is highly toxic to living organisms. Consumption of water that contains chromium 6 can lead to liver, kidney damages, as well as cancer. Scientists have introduced and applied several technologies like coagulation, precipitation, adsorption, and membrane separation to remove these pollutants in wastewater. Over the years, adsorption has been identified as the most highly recommended method to remove the pollutants due to it being cheaper and easy to operate, and as well as being highly efficient. Scientists have also managed to come up with an easy way to remove water pollutants, which is preparing a cheaper anionic absorbent by reacting Moringa oleifera powder with epichlorohydrin and triethylamine as a modifying agent for the removal of chromium 6. In this case, one can ask, what is Moringa? In simple terms, we can explain to them that Moringa is a tree that is mostly common in our households, that it is known for its ability to heal different types of diseases like fever, as well as also improving a human's immune system. In order for us to understand the problem of the water pollution that we are trying to address in this case, let's take, for example, we have a gold mine. They purify their precious metals, and then from there, the water that they use to purify their metals, it contains these heavy metals. They dispose it into what they call it as their waste, or sometimes they just let it to flow with the rivers. And from there, the water leaches into the ground, and from the ground we have people who have bowls, for example. They can consume this water, which is now considered as underground water, and from consuming that water, that is when they will have health problems such as liver damages, cancer, and also kidney damages.
So now let's look at the materials used for this method. Potassium dichromate, which is 97% is used. Sodium hydroxide pellets, which is also 97% pure is used. Hydrochloric acid, which is 37%, and diphenyl carbazide and dimethylformamide, triethylamine, and epichlorohydrin and diethylamine. The study shows that the environmentally safe bioabsorbents can be used for cleaning of heavy metals in water, such as chromium. So now let's look at the preparation of functionalized cellulose of the Moringa oleifera. The MO leaves are collected and washed with deionized water, and then they are dried in the oven for 12 hours at 80 degrees Celsius. Let's look at the method of benched absorption. In a 100 ml reagent bottle, the FMO is added and 50 ml of 100 milligrams per liter of chromium solution is added. The solution is shaken at 200 per meter speed at 25 degrees for 24 hours. Using different pH, dosage, and time, they were used to determine the optimal conditions of different masses of adsorbent, which is FMO indices were from 0.05 and to 0.4, while the concentration of chromium is fixed. So now let's look at the chromium detection using a waste spectrophotometer DPC solution. The solution is prepared by dissolving 0.125 gram DPC in 25 ml of metals and 132 of 5.2% of sulfuric acid is added in a 250 volumetric flask, and it is diluted with deionized water to fill up to the mark. For chromium detection, the DPC solution is mixed with the chromium sample at the ratio of 1:3. It forms the violet-colored complex, the major absorbent, at 520 nanometers using UVS.
After conducting an experiment, the results were also obtained. This adsorption displayed a broad peak at 3,272 per centimeter, which represents the hydroxyl group. The peaks appearing at 2,916 to 2,849 per centimeter were ascribed to aliphatic carbon-hydrogen group. The peak at 1,621 per centimeter indicated the stretch between the bond of carbon and oxygen. The intense peak at 1,020 per centimeter could be attributed to alkoxy group. The adsorption bonds of Moringa oleifera were maintained in the FMO, therefore showing that after the modification of amine groups, the Moringa oleifera structure was not disintegrated. The adsorption by FMO showed a sharp peak at approximately 1,351 per centimeter, representing the stretching between a bond of carbon and nitrogen of amino groups transferred on the surface of FNO. The bands appearing at 1,647 and 1,030 per centimeter were assigned to nitrogen and hydrogen stretching band of amino groups.
Adsorption mechanism. Chromium-6 adsorption mechanism onto FMO was evaluated based on adsorption results and characteristics analysis as summarized in the picture. The pH of the solution is the most important factor which tends to influence chromium-6 speciation and ionic state of the active functional groups of the adsorbent. At pH between 2 and 6, chromium-6 exists as HCrO42- and Cr2O72- in aqueous solution. These anionic chromium-6 species are adsorbed by protonated functional groups of the adsorbent. Real water sample analysis and influence of interfering ions of chromium-6 removal. Industrial water waste from chrome plating, mining and leather tanning, etc. does not contain only chromium-6 but consists of many other ions. In this experiment, the removal of chromium-6 was studied in the presence of the few selected ions like Ni2+, Cu2+, zinc 2+, SO4 2-, Cl-, and NO3- at different concentrations, 20 to 100 milligrams per liter. The study was conducted to investigate the selectivity of FMO towards chromium-6 in the presence of other ions. It can be observed that Ni2+, Cu2+, and zinc 2+ has minor effect on chromium-6 removal. At pH 2, the amine group on the adsorbent FMO surface were positively charged, therefore making electrostatic interaction between cations and adsorbent impossible. The graph shows that the three ions SO4 2-, NO3-, and Cl- had some effect on chromium-6 removal. NO3- and Cl- had a very minimal effect, which is 1.68% on chromium-6 removal. whereas in the presence of SO42-, this chromium 6 removal was slightly affected, especially at higher concentrations at 100 milligrams per liter SO42-. Chromium 6 removal percentage decreased from 99% to 95.02%. This could be due to similar inner and outer sphere complexes for both chromium 6 molecules and SO42-, which can lead to competition of unoccupied adsorption sites of FMO.
In conclusion, the study investigated the effectiveness of diethylamine functionalized Moringa oleifera leaves in removing chromium 6 and bacteria from wastewater. Results shows that the introduction of amine groups onto Moringa oleifera enhanced the adsorption capacity, where it increased to 99% towards the removal of chromium 6 at low pH less than 2. The adsorption mechanism between chromium 6 and FMO leaned towards a chemical behavior than physical. These findings highlight the potential of bio-based materials for sustainable wastewater treatment. The use of Moringa oleifera leaves offers cost-effective solutions, environmentally friendly alternatives, and scalability for industrial applications. So future research should explore the scaling up for real-world applications, optimizing functionalization methods, and exploring other heavy metal removal capabilities. Ultimately, the findings underscore the importance of addressing global water pollution challenges, providing a promising solution for safer and cleaner water. Thank you.
Thank you guys for sacrificing your time and borrowing us your ears and to come and attentively listen to what we have managed to present to you. And moreover to that, would like to thank our lecturers for giving us this opportunity as students to work together and be able to come up with different perspectives into understanding this topic.